Now I want to do more than reliable. So last week we did reliable broadcast. Now I want to talk about causal reliable. I want to make it even stronger. So here's the scenario, and it's a chat application. So a lot of people are typing messages and everybody is receiving, and you have like conversations going on. And to make it work well, it's all reliable broadcast. That means if I send a message, then I know that all the correct nodes will get it. If I'm correct, I know everyone will get it. Or even if I crash, I know all the correct nodes will get it. So that the conversations are going on in a consistent way among all the users. It's not true that somebody will get a part of a conversation and the other person will get not that or some other part. It doesn't work like that. Because it's reliable, all the conversations are going on nicely among all the people in the group. So it's reliable. But reliable is not enough, because a conversation means that you have connections between messages. So for example, here's a little conversation, and the guy is Ali, who's Ali Lutzi. So somebody says, does anyone know where the lecture is today? And somebody answers, it's in auditorium D at the Forum building. And then Ali replies, are you sure it's not auditorium D, not E? So this is a conversation. But this message, the question comes first. So if we get it in this order, if we get Ali's reply first, then it's all mixed up. Okay? He's making a reply, but we don't know what he's talking about. The question comes after. So Mr. X's message here is causally connected to Mrs. Y's message. Mr. X's message caused Mrs. Y's message, because Mrs. Y received Mr. X's message and replied to it. And then Ali received Mrs. X's message and Mr. X and replied to that. So there's an order between the messages. So there's connections between separate broadcasts, okay? But reliable broadcast doesn't do that, okay? Reliable broadcast only looks at one message at a time. I do one broadcast, and then I do another broadcast, then I do another. It doesn't say anything about connections. So reliable broadcast will not solve that problem, because if I have two reliable broadcasts, then nobody is saying that maybe the messages between the two are going to be ordered between them because of the different speeds. Reliable broadcast doesn't say anything about that. So it doesn't solve the problem. So what about uniform reliable? Uniform is much smarter than reliable, huh? Does uniform reliable broadcast solve this problem of conversations? What do you think? Now I'm asking you, yes or no? Does uniform reliable broadcast solve the problem when I ask a question and then somebody replies and maybe I received a reply before the question, which is bad? Does uniform reliable broadcast avoid that? What do you think? Now I'm asking you to think about what uniform does. What do you think? You tell me. No? Why not?
Because it ensures that we get the message, but it doesn't say in which order we get it.
Yeah, but it's stronger than reliable though, huh? So why, say a little bit more. Why is it not enough? Why, I mean, it's not enough, okay? Clearly, uniform reliable is not good enough, but why not? What's really the point? I mean, you're right there.
It's the order in which you get them. The messages.
Yeah, we have to do something about the order. Well, what does uniform reliable say about the order? Nothing, huh?
Nothing, yeah.
Uniform reliable, the only thing it does more than reliable is that it worries about failed nodes. It worries about failed nodes. Huh? But in the example here, we don't have any failed nodes. So in this example, uniform reliable would do exactly the same, okay? They have the same specification, because uniform reliable only does more when you have failed nodes, okay? But here we're talking about connections between two or more broadcasts. So uniform reliable does not solve it at all, okay? Does not. So in order to solve it, we need another way to make the broadcast stronger. And that's called causal reliable broadcast. Remember we talked about causal order, huh? It's the happened before relation that we defined. The one that LSINF2345 defined really early on in the course. So we have to worry about order between messages, causal order, in order to do a chat application, okay? So here's the definition of causal order. So this is very similar to the happened before relation, only now I'm making it specific for broadcasts, okay? It's a little bit different than happened before between events, because when I do a broadcast on one node, it actually delivers on many nodes. And I do another broadcast that delivers on many nodes. So I have to worry about the order of the broadcast and the order of the delivery. So it's slightly different, but basically it's the same definition, huh? So let's say we have two messages, M1 and M2. Both of them are broadcast. Okay? We can define causal order. So M1 is before, causally precedes M2, and then there's three conditions. For example, if process PI broadcasts M1, and then PI broadcasts M2 later. So there's clearly an order. Or PI delivers M1, so M1 is broadcast somewhere else, it's delivered on PI, and then there's another broadcast on PI later. So that's also making a connection. Here we're connecting the delivery and the broadcast, okay? See, a message is delivered on this node, and there's another message broadcast on that same node. That's like a chat, huh? I see the chat, and I make a reply. So the broadcast is like a reply here. And then there's the transitivity. This is what makes it complicated. And now I connect all these links. So if M1 is before M prime, and M prime is before M2, then M1 and M2 are connected. So if M prime replies to M1, and M2 replies to M prime, then M2 has to be after M1, okay? So it's transitive. So we're adding all these extra links. So this is why causality is complicated, it's because of this transitive connection. It can make lots of connections, even between messages that are very, very far away. If there's some causal chain between the two, then they're causally connected, and we have to worry about it. Okay. So that's the causal order. Okay, so that's clear. Now we can define a causal broadcast. So this is only one property. So CO broadcast, causal order broadcast. If a node delivers M1, then it must have delivered every message causally preceding M1 before M1. That means if this node delivers M1, then all the messages causally before, according to our definition, should be delivered before. Okay, so this property is ensuring causality. But actually it's not enough by itself. So what kind of property is this? I'm asking you again the standard question. I'm bothering you again with the standard question. Safety liveness. So what is this? What is this property? There's one thing you see there that immediately has to ring a bell. It's a conditional. If something, then something. That's one thing, huh? And so, what can you say? If something happens, then something else must have happened. So, what is it? Safety or liveness? Why?
I assume it's some good thing.
What is the good thing?
Every message carefully proceeding.
Some good thing can happen.
Is that so?
I'm not so sure about that, though. So we're talking about the past here. If the node delivers M1, then we're talking about something that happened before, huh? Not something good thing that might happen in the future. Huh? You can ask another question here. Can we break this condition? Can we break it? Can we do something that means that this thing will always be false in an execution? Can we break it? Like breaking an egg.
Yes.
How?
If we receive some messages and we've not received one of its causal
There you go.
messages.
If you have delivered a message and some causal before message has not been delivered, it's broken. So this can be broken. So that means it's a safety property. And what's the easiest way to satisfy safety property? How can we satisfy this property? It's a super easy way, always, to satisfy safety properties. Life is dangerous, so how can you avoid all the dangers of life? You basically sit at home in your easy chair and you don't go outside, okay? Which means, so what's the way of breaking, of satisfying this?
Never accepting a message if you've not received its causal.
You can do even less than that.
Oh.
By doing nothing, by never delivering any messages. So if you don't satisfy any time the if, by doing nothing, okay? You can always satisfy safety by doing nothing. If you do nothing, you'll never break.
It doesn't help.
Yeah, but that's because what you mean it doesn't have liveness. Okay? If you do nothing, you have no liveness, but you're safe.
Yes.
You never break. If you don't do anything, you will never break the system. So basically, the if condition is never satisfied. See, so you have to get used to thinking about safety liveness. So a big important hint is the if. Huh? If a property has this if-then structure. Okay, write that down. I already told you. Huh? That's something you have to keep track of. So this is only safety. So we have to attach it to other properties. Okay? But let me give some examples now first of the causal order to give you some intuition. So here is the first condition. So P1 broadcasts M1 and then broadcasts M2. Then M1 and M2 are delivered on P2 and P3. So there's a scenario here on the left, and there's another scenario on the right. So I ask you, this scenario on the left, is it satisfying causal order or not? The one on the left. What do you think? Is it or is it not? Very easy. I need one bit of information. Yes or no? From you. Not much. What do you think?
No.
No. Why not?
Because in P2, M2 is received before M1.
Yes. So the order has changed here. So M1 happened before M2, but here we split them. So this the one on the left is not satisfying causal order. Huh? What about the one on the right? Is it or is it not?
Yes.
Yes. Why?
Well, because P2 and P3 received them in the same order as they were
Yeah.
sent.
Because they received in the same order as what's sent and all the nodes. Delivered, to be precise, they're delivered in the same order. So this is okay. Here's the second one. Now we're talking what's called network order. So the two broadcasts are happening on different nodes. So P1 broadcasts M1, and then P2 broadcasts M2. Okay. So what about the scenario on the left? Is it causal or not?
Yes.
Yes.
Yes. Why?
Well, same as before.
Which it would, yeah, same as before.
M1 and M2 are on the same order for every P.
Exactly. They're in the same order, and all three of them. And it's the order, it's the network order, which means that M1 is delivered on P2, and M2 is broadcast after. What about the one on the right here? What about this one? Okay. Is it causal?
No,
No. Why not?
because P3 is inverted.
P3 it's flipped back. So the M1 should be delivered before M2, but here it's delivered, M2 is delivered before M1. Yeah, so that one is not causal. Okay.
Sorry, is that the
Yes.
same speed for the message leave P1 to P2 and P3?
Ah, the speed.
The same speed?
The message delay. We don't know the message delay. It could be anything. There's no condition on message delay here. So here, the M1 message is very slow, and the M2 message here is very fast. Yeah, it can happen. There's nothing preventing messages.
But if happened, it is not casual.
Yeah, that if you have differences in speed, it's kind of dangerous because you might break causality if the algorithm is not preventing it. Huh? Yeah. So difference in speed is kind of what's causing the problem here. Huh? But we don't have any condition on the speed. No? We're talking about messages with any kind of delivery, any kind of speed, anytime. So here it's more complicated because here I'm showing transitivity. So M1 here is causally before M2 because M1 is delivered before M2 is broadcast. M2 is causally before M3. Okay? And there's a left and a right scenario. So the one on the left, is it causal? So here we're saying, is it respecting the transitivity rule? The one on the left?
No.
Why not? Who said no?
Me.
Why not?
Because P1 receives M2 before receiving M1.
Yes, exactly, because M1 should be delivered before M2, but M2 is delivered before M1. So the one on the left is not respecting causal order. What about the one on the right? There's lots of stuff going on. Don't worry about this message going back in time. It's not supposed to be going back in time. Huh? It's just supposed to be very fast. Okay, so that's not a trap, huh? And neither is this one, huh? So we're just assuming that they can be pretty fast, huh? Okay? So what about it?
Yes.
So, yes. M1, 2, and 3. Here we have M1, and 2, and 3, and 1, and 2, and 3. So the one on the right is satisfying, yeah? Yes, that's right. And one on the left is not. Okay, so that's giving you some intuition, huh? And now, I want to do, before showing the algorithm, I want to do another example of specification engineering. So this is kind of subtle. I can actually have different variations on this causal order property. So here's two versions of it. And I want you to think about the two versions. So the first version is, if PI delivers M1, then PI must deliver every message causally preceding M1 before M1. Okay? But we can make a variation. If PJ delivers M1 and M2, and M1 is causally before M2, then PJ must deliver M1 before M2. So they're slightly different, you see, yeah?
Yes, it's different because if PJ never deliver M2,
Then, yes, if PJ never delivers M2,
this property says nothing.
exactly, and that's exactly right. So both of these are if-then. So I'm telling you how to analyze this. Huh? First of all, both of them are if-then properties. So you have to look at the if condition. So the if condition here, which was exactly right, is that both M1 and M2 are delivered. That means if M2 is not delivered, CB prime says nothing. Okay? If the if condition is not satisfied, this property is not saying anything. But what about CB? Does CB say something in that case? So if M1 is delivered and not M2, CB prime says nothing. But what does CB say in that case? This is subtle, huh? So I'm forcing you to think about specifications. Look how simple this is. It's a simple thing. I'm not even doing complicated mathematics here. Man, you guys are smart guys in the 4th year. It should be very easy, right? To think about this. So assume that M1 is delivered but not M2. So CB prime says nothing in that case. No, yes or no. What does CB say in that case? What does it say? Assume that M1 is delivered and M2 is not delivered.
M2 is after M1.
And M1 is before M2. What does CB say in that case? Oh, it does say something. In that case, CB prime says nothing. But what does CB say?
We know that M2 is definitely not before M1.
No. We know that M1 is before M2. We know that, okay? But M2 is not delivered for some reason. The message is lost. So in that case, CB prime accepts that. It says nothing about that. It doesn't care. But what about CB? So basically, CB prime is true in that case. The property holds, doesn't care. What about CB? So M1 is before M2, M1 is delivered, and M2 is not delivered. What does CB say? What does CB say in that case? Is it holding? Or maybe it's broken. Maybe
It's
CB
holding
is broken.
because in CB we don't really care about what's after M1. We only make sure that every message before M1 is delivered. So if M2 is after M1, the CB is holding.
Yeah, but be careful because this is for every message. This M1 and this M1 is not the same M1. If PI delivers a message, any message, it must deliver every message causally preceding that message. We know that M1 causally precedes M2. Okay? I'm trying to confuse you. So in that case, so it delivers M1.
And we have to make sure that every message before M1 is delivered.
So CB also is saying nothing in that case, huh?
Yeah.
So we can make, so that's good. So I make a small variation now. Okay? I make a small variation. I have M1 and M2. Assume now that M2 is delivered and not M1, and M1 is before M2. In that case, what do the two properties say? So this now, I'm changing a little bit the scenario. M2 is delivered, and M1 is actually before M2, but M1 is not delivered. What does CB prime say?
It's the same.
What do you mean? What does it say?
For CB prime, it doesn't change the... If we change the order, it doesn't change anything because it has to deliver.
So what does CB prime say?
It's holding. No.
Yeah, it's saying nothing. So basically it holds vacuously, yeah?
Yes.
It's not saying anything, actually. It's holding vacuously because if condition is false. What about CB?
But now CB is not holding anymore.
Now CB is not holding, exactly. Because now CB is not holding because for CB, if M2 is delivered, M1 has to be delivered, and it's not. So in this case, CB is not holding. So the two properties are not the same, but you can see clearly they're not the same. So in fact, one of these properties is stronger than the other. That means if one holds, then the other automatically holds. In what direction does that go? If one of the two holds, then the other will guaranteed hold. In what direction is that? If it holds, then holds.
If CB holds, then CB prime will hold.
If CB holds, then CB prime holds. Exactly. Because CB forces all of the ones before to be coming, but CB prime does not force that. But if there are messages coming, that CB prime is saying something, CB will say the same. So CB is strictly stronger than CB prime, okay? So here's a scenario on the left that I'm violating both properties, okay? So again, I have some broadcasts here. So here I have a scenario where I'm violating both. So M1 is before M2, okay, that's clear, huh? But M2 is delivered before M1. So both of these are delivered, which means that CB prime holds. But the order is inversed, so CB prime is applicable, I'm not saying it holds, it's applicable, because both of these are delivered, but it's false. And CB, of course, is false too, because M2 is delivered here, but M1 is not before. But here on the right, we have a case where CB is violated, but not CB prime, okay? So M1 again is before M2, but if you look at P3, M2 is delivered, but not M1. M2 is delivered, but not M1, so CB prime does not hold here, it's not applicable. So it holds vacuously, it's not applicable. Whereas CB is violated because the fact that M2 is delivered means that M1 should be delivered too, according to CB. Okay? So if CB holds, then CB prime will hold. But not in the opposite case. So it's possible for CB prime to hold and CB to be violated. So CB is strictly stronger than CB prime. Okay? CB implies CB prime. So which property are we going to use in our algorithms? If we want causal broadcast, which one do we want?
CB.
CB. I think we want CB because we don't really like, this is not a good case. We want CB, yeah? We want all the causal preceding messages to come in if a message is delivered, yeah? Okay? So this is an example, what I call specification engineering. Thinking hard about the specifications and figuring out the small differences, okay? So that's very important because the whole implementation rests on this, okay? If there's a mistake here, then everything is going to be fundamentally wrong. So you have to be very careful that the specification is good, huh? Okay, you see that? Specification engineering is important, huh? So here's our reliable causal broadcast now. RCO, reliable causal order. So we have the 4 properties of reliable broadcast. Remember, this is the ones we saw last time. The no creation, validity, and so on. And the all or none property. And then we add this CB. So CB is safety, but it doesn't matter because the aliveness is guaranteed from RB, so from these. So CB is just an extra safety property. It means we have to be a little bit more careful not to break the system, the CB. Yeah? We have to worry about order. So some of the executions of reliable broadcasts are not accepted. This is an extra safety condition. Okay? Causality. So that's our specification, and now we can implement it. So we also can have a uniform reliable, so it's almost the same. So the only difference is what happens with failed nodes. So we take our uniform reliable properties, and we are again making sure that we're very safe. So if a node delivers, we're not saying if it's failed or not. Then it must deliver every message causally preceding. Okay? So basically we have the 2 versions. We're adding a little extra safety. Okay? And now we can implement it. So basically we're going to use a layered architecture. We're going to reuse reliable broadcast for causal broadcast. We're going to take the reliable broadcast algorithm and use it as a base. Okay, we're going to build something on top of it. So that's how we're going to implement it. So we don't want to implement it from scratch, huh? So we have reliable broadcast. So we're going to make a causal reliable broadcast on top. Okay? So we're going to use the reliable broadcast kind of as primitive, and we're going to build this extra layer on top. And the same for uniform causal. We're going to use the uniform reliable as underneath. Okay? Uniform causal reliable broadcast, or uniform reliable broadcast. So we just have to add this extra layer that gives us more safety. Okay? So what's the idea of the algorithm? How can we do it? Well, causality means that you have to make connections between multiple broadcasts. So the idea is that we piggyback information on the messages. Each broadcasted messages will have some extra information added to it. Okay? This extra information tells us something about causality. So it's very simple. One simple algorithm is to piggyback all causally preceding messages on top of each message. Okay. If you're efficiency-minded, you will immediately say, well, that's super inefficient. Forget about efficiency in the first step. I know that's very hard, but you have to do that. We'll worry about efficiency later. So this first algorithm, we can piggyback all causally preceding messages on top of each message. So we have a message here, M, and then the message here will be M plus the history. Okay, so the reliable broadcast here is going to have all this causal information added to the message. Okay, and that will make the algorithm simple. So the CB algorithm here is going to be pretty simple because of that. Okay, so this, we call this the fail-silent, no-weighting causal broadcast. So what does fail-silent mean? Again, I ask you, you're supposed to know what it means. Huh? What does fail-silent mean when I say an algorithm is fail-silent? It means it does not need, it does not use a perfect failure detector, okay? No failure detectors. So there might be one inside here, we don't care. But this CRB algorithm is not using, okay? You see, I'm trying to get you guys, because we really don't have enough lab sessions in this course. It's a way of getting you to think, okay? If you understand it now, it's so easy to study. If you understand the things today, it'll be very easy. It's just refreshing. So then it's very easy. So each message will carry an ordered list of all the causally preceding messages. So this ordered list, let me call it past M. It's just a sequence of messages. Whenever a load RB delivers, so RB delivers is here. Whenever load RB delivers, I will CO deliver, so this is the CO delivery, all causally preceding messages before delivering M. That's pretty easy. So all messages in past M that have not yet been delivered, so I have another delivered set here to avoid duplicates, another set here. So if I come here, M plus past M, and if I see that some of these messages in past time have not yet been delivered, I deliver them, all the ones that have not yet been delivered, and then I deliver M. That's pretty easy, okay? And so with my delivered set, I have no duplicates. So if I do like this, the code is pretty straightforward. So the algorithm becomes very, very simple, actually, okay? So here's an example, execution, which I call direct override. You'll see why I call it that. So here I have three processes. This one is doing causal order broadcast, M1, okay. And then I do causal order delivery because This is the first one, so we don't really have to worry. These two red blocks are the causal delivery. Now I do another causal order on the same node, M2. So if you notice here, I have, when I send M2, I have this piggyback. So M1 is causally preceding M2, so it's in the list here, and here also. Notice that this message here is somehow very slow, and this message here is somehow going very fast. So that's totally possible, okay? So this M2 will arrive here on P3 way before M1. So now, what do we do? What do we have to do? It's pretty clear, huh? What we have to do? Well, we can do a P1 and P2 and P3. So here I'm going to be very precise. The RB delivery is happening right here. The RB delivery. This is why I like to talk about delivery and not receiving, okay? RB deliveries happened, but I still have no CO deliveries. So I notice I have not yet delivered M1, and M1 is before M2, so I have to CO deliver M1, and then I CO deliver M2. Okay? And what happens when M1 arrives here? What do I do? What happens when M1 arrives later? Nothing, huh? I do nothing because I've already delivered M1. Okay? So I call this direct override because this past this delivery is overriding this one. Okay? You see? We have to deliver it earlier. That's fine. Okay? So you see how the algorithm works? It's not so complicated, huh? This extra safety condition. We just have to be a little bit more careful about how we deliver. So here's another example. So P1 is doing causal order. But now P2 does the next causal order. Okay? P2 does the next one here. So now, and one is before M2, huh? So now, again, M1 is very slow. M2 is very fast. So again, what do we have to do here? What do we deliver here? It's pretty clear, huh? Right? You guys get it, huh? The guys sitting on that side, the other guys, see, get it too? It's pretty clear, right? Say yes, it's clear. Yes, it's clear. Okay. I call it indirect override because the override is coming from another node. This is kind of sophisticated if you look at it from far away. Huh? P1 is sending a message to P3, but P2 sends a message to P3, and the P2 message is overriding the P1. So P1 is saying, hey, what's going on? Another node is overriding me. So P2 is somehow overriding P1 here. But that's okay, because there's an intermediate step here. So if you only look at P1 and P2, it looks kind of strange, huh? Why is P2 overriding P1? So I call this, just to give you some name, I call it indirect override, because P2 is like, it's not the same node, it's another node is overriding P1. That's okay. It's perfectly possible. It's not a problem, okay? So this is a pretty straightforward algorithm, huh? You can see how the lane structure is very nice, huh? It means all the hard stuff we did in reliable, we forget about it, it's done already. We just have to be a little bit safer. So it's good that we thought a little bit that this is an extra safety property, yeah? All that means is that some delivery orders are not allowed. We have to eliminate certain orders and favor other orders. We have to be safe here, huh? Okay? So we can show the code here. So the code is actually very simple. So the algorithm uses reliable broadcast, has its own delivered list. It has a set, it has a past variable. So on each node, I keep track of all the messages that have been broadcast or delivered on that node. So that's the past of that node. Huh? And when I do an RCO broadcast, I just do an RB broadcast. And I add the message M to my local past, because now I have a new message and all the previous messages are before. Okay? So that's very simple. And then there's just a little bit more code. Okay, that's it. This is the final code. When there's an RB deliver, now I have to be subtle. So first of all, I have my duplicate removal. If M has already been delivered, I don't deliver again. So there's a big if here. And then I look at all the elements in the past, but I do them in order. Okay, starting from the oldest to the most recent. And for each of these messages N, if it's not delivered yet, I deliver it, I add it to the delivered set, and I add it to the local past. Okay? See, this past M is the past coming from the message. Okay? It's the past coming from the message, and the past here is the local past. So when I deliver N, I have to add it to the local past. And I do this for all the messages in past M. And once that's done, I deliver M, I add it, and I add it also to the past, and that's it. So the algorithm is actually very straightforward, huh? You see? It's not so complicated. So in ascending order, deliver preceding messages, append to history, I deliver current message. And then I append to history again. So I have to make sure that I have this little group of three things, huh? When I deliver RCO, I have to add to the delivered and I have to add to the past. Huh? I always have to do that. And then I'm good. Everything's great. So this is the fail-silent causal broadcast. Now, we still have the problem of efficiency here, huh? But at least we have a correct algorithm. That's pretty amazing. This algorithm is actually very smart. Huh? It will work in a distributed system. So it's completely concurrent. We can have on n nodes, we can have anybody doing causal order whenever they want. It's completely concurrent. And it's fault tolerant. Nodes can crash anytime. And this thing will guarantee causal delivery and reliable broadcast. That's actually already a pretty sophisticated algorithm, okay? Concurrent fault tolerant algorithm. But we still have to worry a little bit about efficiency. Okay, we can reason about correctness. And then we can worry a little bit about efficiency. So I'll talk a little bit about efficiency. So let me make a break now. And after that, we'll see how to make this thing efficient. Okay?